आज के लेक्चर में हम बात करेंगे कंडीशंस फॉर सस्टेन्ड इंटरफेरेंस. What we actually mean by sustained interference. Whenever we talk about interference, we have maxima and minima there, right? And sometimes they keep on changing their positions with time, right? Uh, it is necessary that these positions of maxima and minima they remain fixed, right? If they keep on changing, they will mix up and produce uniform illumination, right? So a particular interference pattern in which positions of maxima and minima of intensity they do not change with time, that is called your sustained interference. Now, what are the conditions to observe this sustained interference? First thing is that the two sources, the two sources, they which are emitting these waves, right? They should have same frequency. The waves should have same frequency and wavelength. Second, the waves that the particular source they should be coherent. By coherent here we mean they should have same the waves coming out. They should have same phase or constant phase difference. Right? For better contrast so that we can have a clear bright and dark bands there, right? In order to get so right the amplitude of both the waves that should be equal. The two sources they should be very narrow, right? Actually in case of broad sources, the light is actually this broad a single broad source that actually work as that act as a set of small sources, point sources there, right? If instead of taking a small slit there, if I take a broad source here, right? So every point within this slit that will act as a new source there, right? And these sources, the light coming from these sources, they will have their own interference pattern. Each two sources will give two interference patterns there, and they will overlap, and that will result in general illumination there, right? And your interference pattern that will not be observed there, right? So the source, the particular sources, they should be small, they should be narrow sources, right? And your interfering waves, they must have they must travel along the same direction, only then you will get interference pattern there. At the same time, source should be monochromatic one. Monochromatic means the same wavelength, same color, a single color. Sources, we need to have the sources which are monochromatic, having same wavelength there or same color there. If we in case if we take the two sources of different color, right, the interference pattern from the both, they will overlap, and we will observe only a few fringes will be observed there. At the same time, they should have same state of polarization there, right? At the same time, this particular condition is very clear to you. This as beta is lambda capital D over small d. So this is smaller the value of d, separation between the sources, right? Better will be the fringe width. And at the same time, as beta is proportional to capital D, larger the d. D is your distance between your source and the screen, right? Slits and the screen. So larger the d, better will be the fringe width there. Okay. Next are your techniques of obtaining interference. Right. First technique is getting interference by division of wavefront. Division of wavefront, as we did in case of your Young's double slit experiment. We had two different slits there, right? Light coming from a single slit or single source, right? That is actually split into two parts with the help of two different slits there, right? And uh, these two parts of the same wavefront, they travel with slightly different paths there, and they reunite to produce produce interference fringes there. Okay. अगर हम इसकी बात करें तो डिवीजन ऑफ वेव फ्रंट का हमारा मीनिंग क्या है? इसमें जो हमारी वेव फ्रंट है दैट इज बीइंग स्प्लिट इनटू टू पार्ट्स, है ना? यहाँ पे आपकी जो ये वेव फ्रंट है, this wave front is split into two parts, and these two parts they travel along different paths and interfere at a particular point there, right? They meet at a particular, reunite at a particular point there to produce this maxima or minima there, or interference pattern there, right? So one of the example is your for division of wavefront is your Young's double slit experiment. In addition to this, few more experiments are there. Your Fresnel's double mirror, Fresnel's Bi-prism, Lloyd's mirror. We will be discussing them in the chapter, right? Okay. Next is your division of intensity. Interference by division of amplitude or intensity. It's a simple example is that this division is actually take place by a partial reflection and refraction. Means we will have if we are having a small thin film there, very thin film there, right? A particular wave coming into the film in this way, right? It gets reflected, and a portion gets reflected there, right? And this reflected wave, that also a portion gets reflected there, right? Reflected there, and these two reflecting waves, they reunite to form interference pattern there, right? This kind of division is called your division of amplitude, right? And the particular experiments we will be discussing in this chapter are your color of films, color of your thin films, and neutron ring method, as well as your fringe which are produced by your Michelson interferometer. Okay. Next topic is our Fresnel's Bi-prism. If we talk about Fresnel's Bi-prism, in this method we will have Fresnel's Bi-prism. Bi-prism means instead of single prism, we will be having two prisms, right? And these two prisms, they are actually so placed that they act as a single prism. They are having one of the angle as obtuse one of 179 degrees and two acute angles of 30 minutes each, right? Okay, the source is placed in front of the edge there. This is called a refracting edge there, right? And the light which falls on the lower portion of the refracting lower refracting portion of the prism, right? That will form sorry, light coming from the lower the falling on the lower portion of the prism, right? That will move in such a way that it appears that it is coming from this particular imaginary source B, right? We are actually having a single source there. These two A and B are imaginary sources, right? And the light that falls on this lower portion, right, it moves in such a way, it travels in such a way, it travels in such a way that it appears that it is coming from this virtual source B. At the same time, the light which falls on the upper portion of the biprism, right, it appears that it is coming from the it moves in such a way that it appears that it is coming from the virtual source A there, right? And we will observe due to this reunion of this light on these light waves on the screen there, right? We will observe an interference pattern there, right? Actually, the interference pattern that will be observed within this range E and F there, within E and F, that the particular pattern is your interference pattern. At point C, actually the waves, they are traveling, they are traveling equal paths. So this will be your central maxima, and we will be having alternate maxima and minima, as we got in case of your Young's double slit experiment there, right? Right, in the neighborhood of this this maxima, central maxima there, right? Beyond F and E, beyond F and E means in this particular portion, and the portion above E and the portion below F, right? The particular pattern observed is your diffraction pattern, which will have your these fringes of a bit higher width there, right? Okay, now next is determination of wavelength. This particular experiment that can also be used to find out the wavelength of the light that is actually used there in order to determine that determination of the wavelength of light, right? We first try to write down the try to find out the value of beta. Beta is your fringe width, fringe width. In order to do so, what we actually do here, right? Instead of a screen, there, we will be using a eyepiece there, micrometer there, right? Micrometer eyepiece there, right? And this whole setup that is placed on a on an optical bench, right? I will be uploading a small uploading a link corresponding to this experiment there, related to this experiment there, or rather the link of this experiment there, right? You need to go through that video link there, and it will be better, it will be more clear that what type of setup is actually used in case of your Fresnel Bi-prism experiment there, right? That will make it more clear, right? So all these things, that your source, your Bi-prism, your eyepiece there, they are actually placed on an optical bench there, right? And this eyepiece is so adjusted, it is so moved back and forth, so that we can get a clear interference pattern there, right? Once you get an interference pattern there, right? Now, what will you do? You will move this optical this eyepiece in a direction perpendicular to the optical bench there, right? Right. So with the movement, obviously these the crosswire there within the eyepiece, you will actually you will get this kind of pattern there: dark and bright, dark, bright and dark. This kind of bands, they will appear on the within the eyepiece there, right? And you will be having a crosswire like this here within the eyepiece. Now you will move towards left or right in one direction there, right? Now while you move towards one direction perpendicular to your the setup of your optical bench there, right? You need to count the number of dark or bright bands there, dark white bright bands there. At the same time, you need to measure the distance through which this eyepiece has been moved, right? So the eyepiece is moved at right angle to the length of the optical bench, and number of fringes that pass the crosswire, they are counted. Okay, now this beta is actually total distance moved, how much distance have been moved, and divided by the number of fringes that moved across the crosswire, right? So this particular will have some numerical value, obviously, right? And that value, that is to be substituted for beta there, right? Okay, we know that beta is your lambda d over small d. We have seen it in the earlier article in my last lecture there. We have calculated this formula, we have derived this formula: beta equals lambda d over d, right? From here, lambda is your beta small d over capital D, right? Beta has been measured with the help of this eyepiece, right? And small d is the separation between these two virtual sources, and capital D is the distance this distance of this eyepiece from source, it can also be measured. Capital D as well as beta, that can be measured directly. You can on the optical bench, you can measure the distance between the source and the screen easily, right? The thing is that how to calculate this small d, or as these two sources, these are virtual sources, how to calculate small d. In order to do so, what we will be doing here, we need to place a lens between your biprism and eyepiece. We need to insert a lens here between biprism and the eyepiece, right? Now two possibilities are there. One, when this lens is close to your biprism, right, move it back and forth and adjust it in such a way, no need to once you obtain the interference pattern there, right, you keep the positions of eyepiece and biprism unchanged. No need to change their position, right? You simply insert the lens there, right, it move it back and forth close to biprism first, right, and adjust it to a particular position where two images of these A and B, they are visible, they are seen, right? Once you see those two images, right, you just find out the distance between these two by moving the eyepiece in a direction perpendicular to the length of the optical bench. Let it be d1, right? So magnification is actually given by V by U equals to d1 by d, d1 by d there, right? Okay, by the formula of your optics there. So magnification is your V upon U equals to d1 by d. D is the distance that we need to calculate there, right? Next, now simply move this lens towards your eyepiece, and the two images of these source, these virtual sources A and B, they will be visible once again, right? You just take this lens from this particular position to another position which is close to eyepiece, right? Now this distance will be V, this one will become U now, right? And the magnification will be U upon V. Let the now move this eyepiece in direction perpendicular to the length of the optical bench, right? And this ratio, this V U upon V, that will be now D2 over D2 over D. Let D2 be the this particular distance moved, distance through which this eyepiece that has been moved between the two images, right? Now multiplying these two equations, V cancels with V, U cancels with U, we will be having 1 on the left hand side, and on the right hand side we'll be having d1 d2 over d square, right? So multiplying these two equations, it will result d1 d2 over d square equals to 1, or d equals to square root of d1 d2 there, right? Using the value of beta that we have measured earlier, D from this particular formula, and capital D from the optical bench, right? We can calculate lambda there. Okay, I just stop this particular topic here. Okay, thank you.